Hi there, welcome to section 9.3, which is our last section in Math 148. It's on functions and graphs. I cannot believe we've made it to the end of the course. There's a lot of material in this course, so pat yourself on the back. We've got one more to go. So we're going to jump in. We're going to start by talking about functions, and then we'll get into graphs as we go through the end of the notes. So we're going to start by just playing a little game called What's My Rule? So I would normally do this in a classroom. I always start the notes by playing this game with students. And basically how it works, this is a game that you could play with elementary school students. And you could do this with, students as young as, first grade, really. Your rule would just be really simple, and then as they get older, your rules can be more complex. But basically, the way it works is you ask students, you say, I want you to give me a number. And so you just ask them to shout out a number. And they give you a number. So let's say, students give me number 2. So I say, okay. So I write 2 in the input column. And with little kids, you wouldn't probably call these input outputs X and Y's, but you could still set this up as a chart. So you give me 2, and then I say, okay, well, I'm going to do something with your number. I've seen teachers use little creative machines, so students visualize the number 2 going in the machine, and then, okay, what does this magic machine do to my number? And then it spits out something else. So let's say you give me 2 and it spits out -6. Okay. So then I say, okay, give me another number. Okay, how about 5? So a student gives me 5. And I say, okay, well, the output is -15. Give me another number. Somebody says 6. -18. Give me another number. 10. -30. And what you're trying to figure out is, what am I doing to X to get Y? Okay, so like at this very first step, you could say, well, if you give me 2, maybe I'm subtracting 8. Okay, because 2 minus 8 is -6. So that could be a rule. The rule could be -8. But then it has to work with every single one. So look at the second one. If we take 5 and we subtract 8, we end up getting -3. So that rule doesn't work. So you have to think about what else could be going on between those values. So let's do 2 more. Let's say students give me 20 and I give you -60 in return. You give me 30 and I give you -90 in return. So can you guess the rule? What am I doing to X to get Y? So the answer is that I'm multiplying X by -3. Every time you give me an X, I multiply it by 3, and that's the Y. So the rule is -3. So the way I could write that is I could say Y is equal to -3 times X. So that would be the equation. Now with little kids, you wouldn't write it as an equation. You would probably do a rule that's adding or subtracting, and just to get them to say, oh, you're adding 2 every time, that's great. Let's try another one. So let's say students give me 2 and the output is 4, 6, 36, 7, 49, 10, 100. Okay, notice these outputs in this one are getting really big. So they're growing a lot faster than the ones over here were growing. And at some point, usually, as I'm doing this with Math 148 students in class, somebody will get the idea to give me 0. So what happens if you give me 0? Well, the output is 0. And then somebody a lot of times will say, well, what about 1? If 1 is the input, 1 is going to be the output. 0 and 1 can be really telling and give us some clues. So see if you can figure out, what am I doing to X to get Y? And the answer here is that I'm squaring it. So I'm taking X and I'm squaring it to get Y. Okay. I'm going to do one more. So I'm going to do one that's a little bit harder, more complex here. So now at this point, a lot of times students will just start with 0. Okay, so they give me 0 and I say, okay, output is 3. So at that point, they might be thinking, okay, the rule is +3. Or maybe the rule is times. Well, no, it couldn't be times because you're getting 3. So it's got to be something plus or minus. If they give me 1, the output's going to be 5. 2, the output is 7. 3, the output is 9. 10, the output is 23. 20, The output is 43. And I'm actually using inputs that my students gave me in a previous semester. So these can be anything. These are just random numbers they're giving me. So what am I doing to X to find Y? This would be a great time to pause the video if you want some time to think about that. So this is actually a two-step rule. So we're actually multiplying by a number and adding by a number. And this row right here with the 0 is really telling, because if we're multiplying by something, that's not going to affect us here because 0 times anything is 0, but then I still end up with 3. So this is a clue that there's got to be a plus 3 somewhere, or there likely is in the equation. And then this one down here with the 1, that gives me another clue, because if I'm adding 3, then that means I've got to have a 2 here so that when I add 3, I end up getting 5. Well, how could I get a 2? I could multiply this one by 2. So at this point, I might say, well, let me try this. 2 times the input plus 3. Let's see if it works. So if we plug in 0, 2 times 0 plus 3 is 3. So that works. Let's try 1. 2 times 1 plus 3 is 5. That works. That's what I'm supposed to get. Let's try 2. 2 times 2 is 4, plus 3 is 7, and that's what I got. If you want, you can continue down and check, but they end up working out. So the equation for this one is y equals 2x plus 3. Okay, and then lastly, I'm going to do one more, and I'm going to do this one a little quicker. So I'm going to just give you some inputs, and then the outputs are 2, 3, 5, 18, 102, 402. This one is definitely a lot harder, but things to think about. Definitely think about how quickly the output is growing. So like in this example, the second one, when you gave me 10, or a student gave me 10, I got to 100. Yet the first one I give 10 and I got to negative 30. The second one, when 10 was put in, we get 23. So notice that when we got that really big output quickly, there was a squared term in there. And I noticed the same thing happening here. When you put in 10, you already get 102. So that's close to squaring. 10 squared is going to be 100. 4 squared is going to be 16. 2 squared is 4. 1 squared is 1. 20 squared is 400. Do you notice that when we square the input, the output is really close to that value? Well, how close is it? If squaring 20 is 400, well, 402 is 2 away. Squaring 10 is 100. So 102 is 2 away. Squaring 4 is 16. 18 is 2 away. So see if you can pause the video and think about how you would write that as an equation. And the answer here is going to be y equals x squared plus 2. So you square the input and then you add 2. So these are just, a couple of examples. There's lots and lots and lots more. These can be very tricky, so don't feel like, if you didn't get those as I was talking about them, that's totally okay. These can take some time to think about. So I'm doing them a little bit quickly here just as an example, but, definitely don't expect yourself to get them right away. And some of them you just have to walk away and come back and try again later. So let's jump into the first example, example 1, and we're going to try to, this relates to what we were just doing, in a sense that what we're trying to do is to describe a rule for assigning each element of the input to the output. So basically what's happening here, I'm taking 46 and I get 23, 18, I get 9, 120, and I get 60, 7, and I get 3.5. So what is happening to the input? And we're taking the input, and you could pause the video and see if you can figure this out on your own first. We're taking the input, and we're dividing by 2, and that's going to give us the output. Okay, and there's lots of different ways you could write this. The way I wrote it is not like an equation. If you want to write like equation, you could say x divided by 2 is equal to y. But I think this way that I wrote it right here is a nice way to start this section. Let's look at this second one. So what are we doing? What's the relationship to the input? So this shape and the output, 9. This shape here and an output of 7. This shape here and an output of 7. So notice both of those shapes actually go to 7. So see if you can figure out what's happening there. So with that one, we're taking, oh, it looks like I'm freezing up here. All right, there we go. So what we're doing here is we're taking, they're taking the area of the figure. So the area of the input shape, and that's giving the output. So the area of this shape is 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, so it's linked to the number 9. Let's look at this one. So input, Florida is connected to Tallahassee, Michigan, Lansing, New York, Albany. So we're taking the capital of the input, and that's giving us the output. And then last, what are we doing here? So we've got, it looks like an ordered pair, and that's linked to one single number. So what about the ordered pair? How are we getting that single number? Looks like we're taking the sum, we're adding them together, sum of the ordered pair, and that's giving the output. Okay, so what these are doing is it's getting us used to thinking about what a function is. So a function is two sets. So in these pictures, the sets are the circles. It's an input and an output, and then there's a rule that assigns each input to exactly, and I'm going to highlight this here. Let's see, I got a highlighter. Exactly one output. Okay, that's really important. The exactly one output. Because if there's not exactly one output, then we don't consider it a function. So all of these examples above, if you look at all of the inputs go to exactly one output in this example. So like the 7, for example, doesn't go to 3.5 and also 60. It only goes to 3.5. So this one is a function. For this one up here, now notice there's 2 arrows going to 7, but that's actually okay because the rule says that each input, so for example, this shape looks like an L that's fallen down, only goes to 7. It doesn't go to another number. This shape only goes to 9. This shape only goes to 7. This shape only goes to 4, and this shape only goes to 8. So we're going to say this is a function. If, for example, this shape up top went to, I don't know, 9, I'm just making this up, then we would say, no, it's not a function. Down here, these capitals all go to one, states all go to one capital, so this is a function. And then the same thing here, each ordered pair only is assigned to one output, so this is also a function. Another way of trying to figure out if a relation is a function is we ask ourselves the question, can the first element be assigned to more than one second element? If so, then it's not a function. So are the rules above functions? We've already talked about that. What's an example of two sets that are not a function? So let me draw you a picture because it's good to have an example of what that looks like. So let's say you had a circle, we'll call this, we'll say that this is the input, and then this is the output, and let's say we have numbers 1, 2, 3, and 4, and I'm just making these numbers up. There's no significance to what they mean. And let's say 1 was linked to 5 and it was linked to 10. Let's say 2 was linked to 15, 4 was linked to 15, and 3 was linked to 15. This would be not a function, so not a function. And the reason is, so this would be a great place, pause the video so you can figure out why this is not a function. Is it because 1 is going to multiple outputs? Is it because there are multiple inputs going to 15? One of those is true and one of them is not. So the reason that this is not a function is because the number 1 input is going to more than one output. That is the reason. It's okay that 3 and 4 both go to 15, but it's not okay that the 1 and the 1 goes to 5 and the 10. So that's an example of not a function. So let's look at some examples that are numerical, so there's not a picture for these, it's just a description. So example 2, are the rules for the given sets functions. Each person is assigned to his or her own social security number. So just to get a visual, if you need one, you've got input and output. Output is social security number. And then input, these would be people. So every person in the United States, so imagine, okay, we've got somebody's name, is assigned to one social security number. So you have another person assigned to their own social security number. So ask yourself, is it possible for one person legally to have more than one social security number? And the answer is no. So you say, yes, this is a function because every person is assigned to only one social security number. Okay, let's look at this one. Each amount of money is assigned to the object it will buy. So, for example, let's say we have a dollar amount, $5. Is that assigned to only one item? So is there only one item in the world that $5 could buy? And the answer is no. $5 could buy a lot of different items. So $5 could buy a box of cereal. It could buy a loaf of bread. It could buy maybe a expensive coffee. I mean, there are lots of things. It goes on and on and on. So we're going to say for this one, this is not a function because the input can go to more than one output. And then lastly, each pencil is assigned to its length. So if you have a pencil, visualize having a pencil, okay? If you take a ruler, you can measure this pencil, okay? Figure out how long it is, and then assign it to its length. So for example, we could assign this to, I don't know, 15 centimeters. So the question is this one pencil, can that be assigned to more than one length? So is it possible for it to be 15 centimeters and 10 centimeters at the same time? And the answer is no. Every pencil and every object out there, when you measure it, has one length. So we're going to say this is a function because each pencil is assigned to one length. Okay, so now we're going to continue. Example 3, we're going to start writing algebraic rules. So we're sort of working our way up to dealing with algebraic functions. So A says f of x, so we call this symbol, let me just write this down, f of x. So it says f of x is how you say that. Is an output element, and each input element is assigned to 3 more than twice its value. So first of all, if f of x is the output, then that means x is the input. So if f of x is output, then the x, which is always whatever variable is inside the parentheses, that is going to be the input. And so we want to try to write a algebraic rule so that each input, which is x, is assigned to 3 more than twice its value. So how do you write 3 more than twice its value? Well, 3 more than, so plus, twice its value would be 2 times x. So 3 more than twice its value, and we're going to set that equal to f of x. So the way you say this is f of x equals 3 plus 2x. Okay, next one. You could pause the video and try this one on your own. G of x is output, so that means x is input, and each input element, so x, is assigned to 1 more than 4 times its value. So 4 times its value. 1 more than 4 times its value, and that's going to be g of x. Okay, so these are all functions. A function is just a fancy way of saying there's this relationship where you have inputs and outputs, and if it's a linear function, okay, that's a function whose graphs are lines. Excluding vertical ones are called linear functions, and let's talk about why it's excluding vertical ones. So if we think about what a graph of a line looks like, there's lots of different pictures, but if we think about just our average, I'll just make one up there, that red line, that we would call linear function because each input, so the inputs are on the x-axis, so if we consider like each one of these inputs here is assigned to one output. So for example, x equals 1 is assigned to a point on the graph. Let's say this is 2. So this point right here is the point 1, 2. X equals 2 is assigned to another point. Let's say that's point 2, 3. X equals 3 is assigned to a point. So every single x on the axis, even over here, x equals -4 is assigned a point. It's just down below, it's a negative. Each x is assigned to only one y. The only time that does not happen is when you have a graph that's vertical, and this is why. So let's think about what a line would look like if it's vertical. Well, let's say this line crosses at let's see, looks like 1, 2, let's say that's 3. So x equals 3. Let's think of where all the points are on this line. So you've got points, infinitely many points on this line. Well, that means that x equals 3 is assigned to infinitely many y's. So for example, there's the point 3, 1 on the graph. There's a point 3, 2. There's a point 3, 3, and 3, 4, and 3, 1,000,000, and 3, -1. The number 3 is assigned to many, many different y's, so this is not a function. All other lines are going to be functions. So let's jump in and do an example where we can look at this from start to finish. So example 4, a taxi meter starts at $1.60. So before you even go anywhere, it's $1.60, and then increases at a rate of $1.20 per minute, or every minute. Let M represent the number of minutes and CM represent the total cost in dollars. So I've provided a table over here. So M, this is minutes, and then this is cost. Write an equation for the total cost as a function of the number of minutes. So if we want to write it as a function, that means we have to start with the function notation, which is C of M. So remember, C of M is just a fancy way of saying cost. So if you want to find the cost of how much it's going to be to take a taxi ride, well, let's write a function. So we know it's going to cost $1.60, so we might as well write that down. And then it's going to cost additional money if you go anywhere. So generally, if you're getting in the taxi, you're going to go somewhere. So how much is it going to cost? It's going to cost 100, or not 100, that'd be a really expensive taxi ride, $1.20 for every minute. So anytime you have a rate like this, like $1.20 per minute, that means that you're going to multiply that rate times X. So X is the number of minutes. So however many minutes you ride, you're going to multiply it by 120, add $1.60, and then that's going to give you your cost. So for example, let's go ahead and we'll fill out this table. So let's say you don't go any minutes in the taxi. What we can do is you can use that equation if you want, $1.60 plus 120 times 0. So you don't go anywhere in the taxi, but you literally just open the door and get in. And so when we work that out, you're going to pay $1.60 if you don't spend any time in the taxi. Let's say you go 1 minute. Well, you're going to pay $1.60 to get in plus $1.20 times 1 minute. So that's $2.80. If you spend 2 minutes, you're going to do $1.60 plus 120 times 2, and that's going to give us $4 in the taxi. And I'm going to keep on going, and I'm going to fill in these remaining numbers. So $1.60 plus 120 times 3 would be $5.20, and $6.40, and $7.60, and $8.80, and you can keep going if you want. You might notice that every time we jump up a minute, it's just increasing by $1.20 because that's the rate. So as long as I'm making the minutes go up by 1, then these outputs are going to go up by $1.20 each time. So if you want, you can just use that pattern to fill in the table. So now for part B, it says graph the CM function. What does the y-intercept mean? So we need some axes. Now I'm looking at this since the problem has to do with getting in a taxi. It really only makes sense to deal with a positive number of minutes. So if you want to do your axes right in the center, you can. Another way to do it might be to do something like this, where you have the majority of your graph in quadrant 1. And we can label, so CM, or the cost, is going to be, that's the y variable, and then number of minutes is going to go on the bottom. And then we're going to need to find a scale. So I think, it might make sense if we wanted to just do every box could be 1 minute. So, and then we could just do on the y-axis, every box is $1. We'll just make it simple. So now I'm going to plot these points. So all of these numbers in the table, these are all coordinate pairs. So 0, comma, $1.60. So there's my first point. 1, comma, 280. 2, comma, 4. 1, 2, 3, 4. 3, comma, 520. 1, 2, 3, 4, 5, and a little bit more. 4, we got 4 is going to be 1, 2, 3, 4, and then 640. So 1, 2, 3, 4, 5, 6, and a little bit, almost halfway. And then we've got 5 is going to be 760. 1, 2, 3, 4, 5, 6, 7. And then 6 is 880. And then we can keep going if you want to, but at this point, I'm going to try it to make this straight. Just get a straight edge and you can connect it if you'd like. So it asks, what does the y-intercept mean? So, it says, what does c sub 0 mean, which is the y-intercept? So c sub 0 means what happens if x equals 0, or in this case it would be m, number of minutes. So let's look at that for a minute. So here's the y-axis, and here is, this point right here is c sub 0. It's asking if we plug 0 in, what do we get? Well, c sub 0, if you plug 0 in, is equal to $1.60. Well, what does that mean? And I kind of already touched on this. It means that if you spend 0 minutes in the taxi, it costs $1.60. Now that seems kind of silly because it's like, well, if I'm not getting in, why do I have to pay? Well, I guess in simpler terms that make more sense, this really is just a startup fee. So we encounter this all the time in real life, where before you do anything or have like a certain service, you have to pay a certain amount of money to sort of start up. So that's what that would represent. And that is that y-intercept, or we could call it the m-intercept. What about c sub 4 or c of 4? So c of 4, we can look at the table. When you plug 4 in, you get $6.40. Well, what does this mean in terms of the problem? Well, it means that if I go 4 minutes in the taxi, it costs $6.40. Okay, so example 5, we've got a couple of graphs here that are already drawn for us. So the Leaky Boat Boat Club charges $6 per hour to run a canoe. If you are a member of a club, there's no initial fee. Non-members who are out-of-state residents pay an initial fee of $6, and out-of-state people pay an initial fee of $15. The graphs of these rates are shown below. So that's a typo there. It should be these. Indicate on the graph which line refers to members, non-members, and state residents, non-members and state residents, and then out-of-state people. So I want you to, it looks like I'm freezing up a little bit here, but we can still see it. I want you to see if you can figure out which one of those lines, blue, green, and red, goes with each group of people. And you can pay attention to things like, well, where do they start on the y-axis? And then remember from the last section we talked about slope. If these lines are parallel, it means that they have the same slope. So if the slope is the same, slope can often represent the rate that something that a company is charging. So think about that for a minute. So I'm going to go ahead and mark where these y-intercepts would be. So this one has a y-intercept of 0. This one has a y-intercept, I'll just write a little bigger, 6. So, and this one has a y-intercept. It looks like these boxes are, if this is 6, then each box is 3. So 6, that would be 12, and then another 3 would be 15. So we got y-intercepts of 0, 6, and 15. And if I look at the description, so I see a 15 here. Let's just jump and do that one. So out-of-state people pay an initial fee of $15. Well, that y-intercept starting at 15, that's your initial fee. It means before you do anything, so on the bottom here, this is hours. Before those people do anything, they're at $15. So I'm going to say this blue line is going to be, that would be out-of-state people. So this blue line right here, that would be out of state. And actually, you know what? I'm going to write this over here, out of state people. Okay, and then I see $6. So let's look at for an initial fee of $6. So it looks like non-members who are state residents. So we're going to say non-members okay, who are state residents are going to be that $6 people. And then if you're a member, there's no initial fee. So for the member, that's going to be this last one. I'm going to write member. And the reason this is a member is because it starts out at 0, so no fee. For Part B, how much more will it cost an out-of-state resident than a club member to rent a canoe for 3 hours? So let's use the graph. So let's look at the not the denominator, the x-axis, so 3. So let's go down to 3, and then we're comparing out-of-state and club member. So I'm going to start at 3, and I'm going to go up to out-of-state, and I'm going to put a dot. And then a club member is going to be right here. So let's see what we can do is we can go over and read just by looking to the left. So it looks like a member is going to be charged $18, and then out of state person is going to be charged, it looks like between 30 and 36, so $33. Okay. And we want to know how much more are they going to pay there. And it looks like, oh, and you know what? And it looks like, so if we just figure out the difference between these two, it looks like $15. So $15 more. And the other thing that we could do too is we can just look at between these points how many boxes. So 3, 6, 9, 12, 15. So they're $15 apart. And it looks like I put this in that should be down here. And then for 5 hours, let's do the same thing. So I'm going to go on the x-axis where I see 5, and I'm going to go up here and I'm going to indicate there's the member, and it looks like members would cost $30. And then if I go up here to out of state and we go over 42 and another 3 is $45. So it looks like that's 45. And again, it's $15 difference, or 3, 6, 9, 12, 15. And really, it doesn't matter what number of hours I'm using the canoe for. They're always going to be $15 apart. So $15 more regardless if it's 3 or 5 hours. Indicate the portions on the graph that correspond to those differences. So I just did that. So we look this vertical distance here. Let me grab a red here so it's easier to see. But this this vertical distance, that's your $15 because each box is 3. How much more will it cost a non-member state resident than a club member to run a canoe for 6 hours? Okay, so I'm going to erase this and I'm going to go to 6 hours. So I find 6 hours and I go up here. Okay, and then I'm looking for non-member state resident, so that's my green line, and then a club member. So it looks like this distance. Now what I could do is, before even figuring out the cost, I can just look and see how far apart these are. So it looks like they're 3, 6 apart, so I'd say $6. If you wanted to, you could also answer it in a different way. Whoops, that erased. You could go over and figure out, well, how much would it cost a member? It would cost $36 to run a canoe for 6 hours. How much would it cost this non-member state resident? And it looks like it would cost $42. So then I can find the difference between those and I end up getting 6. So the next part is nonlinear functions. So let me just back up and recap right here. You can see from this picture right here, we're dealing with linear functions because we have lines, and the same thing is true with this taxi example. We also have a line there. So now we're going to jump into something that's not linear. This would be a great spot to pause the video, and if you have a piece of paper handy that you don't mind folding up and tossing when you're done, why don't you go grab that? So when you're ready with your piece of paper, what I'm going to ask you to do is fold your piece of paper in half. And if you fold the piece of paper in half, how many different regions are now on the paper? So for example, you take, an 8 by 10 or 8.5 by 11 sheet of paper, just a regular sheet of computer paper, and then I want you to fold it in half. So if you bend, if you fold that top half down, and you can also do it sideways. It doesn't matter how you fold. You can fold hot dog or hamburger style, but as long as you're folding, once you fold it and you make that crease down the middle, how many regions do you have left? Or do you have? So you should have 2 regions. And then we're going to go ahead, and I'd like you to do the rest of the table. So what this says is, okay, you're going to fold it twice now. So you're going to fold it over so that now it's folded this way, and then you're going to fold that in half. So you're going to fold, and then you're going to unwrap it. So your paper looks like this, and you're going to see that you have creases, and there should be 4 regions now on the graphs or on the paper. So if you fold it twice, then you should have 4 regions. Do the same for 3 and 4. So if you fold it 3 times, you should get 8 regions. If you fold it 4 times, you should get 16 regions. If you want to fold it 5 times, I did that just to keep going, you end up getting 32 regions. It gets a little hard to fold at that point because your paper gets pretty thick. But what we're going to do now is we're going to graph this. So I'm going to graph number of folds on the x-axis and then number of regions on the y. So if I have 0 folds, I've got 1 region. 1 fold, I have 2 regions. 2 folds, I have 2, 3, 4. Whoops, it looks like that escaped. 1, 2, there we go. Okay, and now I'm going to go 3, 1, 2, 3, and I had 8 regions. 1, 2, 3, 4, 5, 6, 7, 8. And then 4 folds, and I'm just getting the numbers right from the table. So 4, 16. So I go over 1, 2, 3, 4, and then up 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then with 5, I can't even graph 5 because it's way off the graph. But I can connect these and make a graph. So notice this is not a line. So it's a non-linear function. It gets pretty big pretty fast. Okay. This is what we call, so on the side here I have this question, is this graph discrete or continuous? Let's talk about what those mean. So a discrete graph is a graph who has, it's not a person, it's a graph that has distinct x values and y value combinations or pairs for those x's, and the in-between spaces don't really make sense. Another way to think of this is that the points are separate. So I'm just going to write down points are separate. And what does that mean? It means if we look at the points on this graph, so we've got, try to get a different color here. When you think about what these points represent, they represent number of folds. And if you ask yourself, does it make sense to have 1.5 folds or 2.5 or 3.33, 4, 5, 6 folds? It does not. So only whole numbers make sense to describe the number of folds. So we call this a discrete graph because we really are interested in just these separate points and not interested in the in-between spaces. And so you can see that the in-between is blue and then the points are red. Now, if you look this up online, so if you just Google discrete graphs, discrete versus continuous, most of what you'll find are descriptions of graphs that are set where the points are not connected. So I could say here that usually with discrete graphs, points may not be connected. Whereas continuous graphs, they are always connected. Here, I decided to connect the points because I still think it makes sense to connect them to show a pattern and to show the general direction of where the graph is headed. So if for some reason, you were interested in 6 folds or 7 folds, you know that you'd be up here somewhere because you can see the general pattern of the graph or the general flow, the direction that it's flowing. So let's go on to the next one, and then I'll come back to the continuous part when we have an example of that. So if x is an arbitrary number of folds and f of x is the corresponding number of regions, what is the algebraic rule for the function? So for this one, what you're going to want to do is we're basically trying to figure out that rule like we did in the beginning here. So we're going to start with f of x, and you're going to try to figure out what do we do with the x? I'm going to come back up to the table. What do you do with the x value to find the y? And so let me just, oh, you know what? I didn't mean to erase all of those ones below. Here, I'll just fill that in real quick. 4, 8, 16, and this is 5 and 32. What do you do? How are 0 and 1 related, or 1 and 2, or 2 and 4, 3 and 8, 4 and 16, 5 and 32. And remember that we're trying to find the same rule. So if you notice, oh, 4 squared is 16, that's great. But the problem is 5 squared is not 32. So that rule's not going to work. I will give you a hint, and it does have something to do with an exponent in there. So if you want to pause the video and think about this for a little bit before you hear my answer, this would be a good time. So the rule, what we're doing here is we're actually taking 2 and raising it to whatever number x is. So for example, 2 to the 0 power is 1. 2 to the 1 power is 2. 2 to the 2 power is 4. 2 to the 3 power is 8. This is a hard one. 2 to the 4 power is 16. It's not one that comes easily for a lot of people, and it's okay if it didn't come easily to you. If you got it, that's awesome, but the rule is going to be 2 to the x power. This is what we call an exponential function. So we talked about how linear functions are lines. It's just, oops. Man, I am having all kinds of problems with my pen today. Exponential function. And an exponential function is when the variable x is an exponent. So when the variable is an exponent. And then in general, the shape of exponential functions usually look like something like this, or that's what we call exponential growth or exponential decay. So in this case, we're growing, so it's exponential growth. And then part E, the graph shows the number of regions appear to be doubling for each new fold. How can the paper folding activity be used to explain why the number of regions will double? Well, if you think about it, every time you fold the paper, it folds all of the existing regions in half, basically creating twice as many regions. So if you have, for instance, actually I don't need to use dashes, I can just draw a rectangle. Let's say you have 4 regions, for example. Well, when you fold that in half, and when this is folded, it's going to be much smaller. Every single one of those regions is cut in half. So this one's going to cut in half, and these 2 are going to cut in half, and now we're left with 8 regions. This is definitely easier to understand if you have a paper in front of you. So if you're struggling to understand what I'm saying, I would definitely get a paper out and be folding there. And this activity is it's an experiment to show us how real life data can be modeled with an exponential function. So let's jump into D, so interpreting graphs. So now we're going to be given the graph and we're going to be asked some questions about it. So for example 7, the middle school sponsored a dance and the graph of their revenue is a function of the number of tickets it sold below. So the order and how they say this is important. So if revenue is a function of number of tickets, it means the number of tickets is the independent variable, or it's on the x-axis, and then revenue is going to be on the y-axis. After the sale of the first 100 tickets, the cost is increased as shown by the steeper portion of the graph. So if you look at 100 tickets, which is at the bottom here, and you go up to the graph, you can notice that the graph all of a sudden after 100 gets a little bit steeper because this is an increased rate. So think of increased slope, or in this case it's cost of tickets, but the slope is increasing so it becomes more steep. Is the graph continuous or discrete? So I want you to think about what I said before. So we can jump back real quick. Discrete points are separate. So the in-between of those points doesn't make any sense. So let's think about this in terms of number of tickets. So we can sell 1 ticket, 2 tickets, 20 tickets, 60 tickets, and there's a bunch of points on the graph here. Ask yourself, does the in-between make sense? So for instance, I don't know, so 1 ticket, I'll write it like this, and 2 tickets, does the in-between, does that make sense? Do we want to know the cost of 1.5 tickets or 1.75 tickets or 1.99 tickets? And the answer is no. We only want to know the cost of 1 or 2 or 3 or 4, but not in between. So we're going to call this a discrete graph because only those whole number amounts of tickets make sense. And then B, what is the revenue and the cost per ticket for the sale of the first 100 tickets? So let's look at what the graph looks like. So at 100, if we go up to the graph and then we read over here, it looks like the revenue for 100 tickets, so revenue is $200. But that's for 100 tickets. So we're asked, what is the cost per ticket? So if it's $200 for every, remember for every is like our ratio, for every 100 tickets, if we divide these two numbers, then we're going to get the cost per 1 ticket. So $200 divided by 100 is $2. So $2 per ticket. So let's think about that. If we sold 100 tickets, $2 a ticket, 2 times 100 is $200, and that matches up with our revenue. And then for the second 100 tickets, so let's go over, so we were at 100, now I'm going to go to 200, and I'm going to look at my revenue. So for 200 tickets, it's $500. Now we have to be careful here, and this would be a great place. You could pause the video and try this on your own. We have to be careful here because the $500 doesn't mean the revenue from 100 to 200. What it means is from 0 to 200 tickets. So we already know that the first 100 tickets, we made $200. Okay, and I'm going to use a different color. So we made $200 for the first 100 tickets. And then for the second 100 tickets, if we made 500 total, it must mean that this is 300. So for the second 100 tickets, our revenue is $300. And just like before, if we want the price per ticket, we can take the ticket cost divided by the ticket. 300 divided by 100 is $3 per ticket for those for tickets 100 to 200. And then if f of x represents the revenue for the sale of x tickets, find f of 50 and f of 150 and give the answers as part of complete sentences. Okay, so let's do that. So f of 50, 50 is our independent variable, which is number of tickets sold. So I'm going to erase this so that I have some more room. And it means I'm going to go find 50 on the x-axis and find what y would be. So it looks like 50 it's in between 40 and 60. So I'm going to come up here and I'm going to read over, and it looks like $100. So f of 50 is 100. What that means is 50 tickets yield a revenue of $100. And then f of 150 means if I go to 150, which is between 140 and 160, and I go up to the graph, and then I go over, it looks like it's in between those two boxes, so it looks like it's about 350. So what does that mean? And I'm not going to write this one out, but I'll just say in my complete sentence that if the middle school sells 150 tickets, then they will earn $350 in revenue. All right, so example 8, we're down to our last example here. The following graph shows a distance in meters, s of t, as a function of time, t seconds, over a 15-second period following an inline skater's trip through the park. Okay, so A, when speed is constant, speed is distance over time. Label the graph with the skater's relative speed, slowest, fastest, not moving. So if we look at all the different parts, so for example, we could look at this, and then we could just leave the middle, just leave that blue, and then we can make this red. So I want you to label these. So what's we're going to go which part, green, blue, or red, is the slowest if this means distance. Okay, so from here to here, the skater went from 0, which is the starting, to 80. So it went 80 meters in 8 seconds. From here to here, the skater didn't move at all because it stayed at 80. From here to here, the skater went from 80 to 160 in, it looks like, 11 to 15, so 4 seconds. So the slowest section would be well, the not moving section, we'll start there, would be here. So not moving because the distance is not changing at all. It's staying constant. The slower of these two, just think, well, which one has the fastest or the higher slope? That's going to correspond to a faster rate. So since the green is not as steep, we're going to say this is the slowest, and the red is going to be the fastest. How far did the skater travel during the first 8 seconds, and how fast is she going? So starting from 0 to 8 seconds, it looks like she went 80 meters. And if we want to know how fast, we're going to use this formula, distance divided by time. So she went 80 meters in, we can just look at the bottom, it looks like 8 seconds. So 8 seconds. 80 divided by 8 is 10, and then the rate is going to be meters over second, because that's how I divided. The meters were on top, seconds on bottom. So she was going 80 meters per second. How far did the skater travel in from the 8th second to the 11th second? So it looks like that's the not moving part. So how far did she travel? Well, at 8 seconds, she was at 80, and at 11 seconds, she was at 80, so she wasn't moving at all. So 80 meters. And we could say she was going 80 meters per second because she wasn't even moving. And then how far did the skater travel from the 11th second? So that looks like this is 11. So from here to here, it looks like she started at 80. We're going to look over to the y-axis at 80, and then at the top when she finished, she was at 160. So 160 minus 80, it looks like she traveled 80 meters. So 80 meters. And so that's the same distance as that first section, but let's look at why we're saying this is fastest. So her rate is going to be 80 meters because that's how far she traveled, but then let's look at the seconds. She started at 11 seconds and ended at 15. Well, 15 minus 11 is 4 seconds. So she went 80 meters, but in 4 seconds, which is why it's appearing so much faster on the graph. As 80 meters in 4 seconds is faster than 80 meters in 8 seconds. So if we divide 80 by 4, we get 20 meters per second. So she was going twice as fast in this red section compared to that green section. Is this graph continuous or discrete? So this is where we want to ask ourselves, like in the past, we've dealt with like ticket sales, for example, or folds of paper, and we said it didn't make sense to have an in-between number for folds of paper or an in-between number of tickets. Now with time, does it make sense to have an in-between time? Can we measure time with a number in between those whole number intervals? So for example, does it make sense to say how far did she travel in 1.5 seconds? Or how far did she travel in 3.75 seconds? Or how far did she travel in 6 1/3 seconds? So 6.3333. And the answer is all of those make sense because we can measure time in an interval with as many decimals as we want. So I'm going to say this graph is continuous. So it really makes sense in this one to not have separate points, but just have that continuous line there. And then we're going to determine the equation for each part. So we've got, this is linear in parts, but each part is going to have a different equation. So just like we did before, I'm going to go ahead and I'm going to label these with a different color. So for this green part, this very first section, we're going to say so when t is between 0 and 8, what is the equation? So S of t. So It looks like, you can do this in a couple of different ways. One of the ways you can do this is you can just look at the slope and you can look at the y-intercept. So this has a y-intercept of 0, and then it looks like it's going, up 80 over 8 or up 10 over 1. So it looks like the slope is is 10 over 1. Another way that you can do it, and this is nice because this will work in all of them, is you can identify 2 points. You can say 0, 0, which is here, and then this is 880. And you can go ahead and you can find the slope that way. So if you didn't want to count, you could subtract the y's. 0 minus 80 is negative 80, divided by 0 minus 8 is negative 8. And if you divide those, you end up getting 10. So if it's got a y-intercept of 0 and a slope of 10 meters per second, which we found out in B, so we already calculated that, we can say that S of t is 10t. So 10 is the slope, t is our independent variable, and then there isn't a y-intercept because it crosses at 0. So this says we can call S of t equals 10t. And if you're not sure, you can plug in a value. So if we plug in 5 times 10 is 50, and if you look at 5, you end up getting 50 on the graph, so that confirms that. This next one, let's think about how do you write an equation with a horizontal line. So we talked about this in 9.2 in our last section. So if you have a horizontal line, you want to look at where that line is crossing that y-axis. So it's always at 80. No matter what the input is, that blue part is at 80, just from 8 to 11, which we know right here. So the equation for that is just going to be 80. And then last but not least, that red part, I'm going to identify, this one's a little bit harder because if you were to extend this, if you were to extend it down to try to find where the y-intercept would be, it looks like the y-intercept would be negative, but it's really kind of hard to estimate that, way harder than the green one, which is very clearly crosses at 0. So for that one, I am going to identify 2 points on that graph. So it looks like this would be a good point and that would be a good point. So we've got 1180 is 1 point, and then this point here is 15,160. And so I'm going to find the slope for those. So I'm going to subtract the y's. 80 minus 160 is negative 80. 11 minus 15, I'm going to put that on the bottom because remember the y is up, the y is on top. So 11 minus 15 is going to be negative 4. Negative 80 divided by negative 4 is a positive 20. So we know that the slope, y equals mx plus b, so 20t is going to start there. But I need to know my y-intercept. So let me go ahead, I'm going to erase some of this so I have some room to write. So I'm going to write y equals mx plus b. So y equals mx plus b. And I'm going to take one of my points. I'm going to pick the 1180. I'm going to make 11 the x and 80 my y. So I'm going to plug 80 in for y. The slope is 20. X is 11 plus b. And I could have chosen 15, 160. It doesn't matter. You'll get the same b regardless. So I'm going to do 20 times 11, and I'm going to go ahead and I'm going to solve for b. So I've got 20 and 11. I'm going to multiply those. I get 220 plus b equals 80, and then I subtract 220 from both sides, and I get negative 140 for b. So my equation is going to be y equals 20x minus 140, but I don't want to use y and x. I'm going to use s of t equal 20t minus 140. If the function notation is throwing you off, like the s of t, if that seems confusing, then just don't use it. Use the y and x. Well, you have to use it in the end because it asks you to, but use the y and x in the beginning like I did, and then you can just replace it for s of t and t at the very end. So to fill this in, we're going to have 20t minus 140. So remember that finding equations, if you want some more examples of this, then just look in your 9.2 notes because we're using the same strategy, but just by picking 2 points and then going ahead and finding the equation of the line that way.